It is my pleasure and pride to present our speaker today, Dr. Dilip Krishnaswamy. He is an extraordinarily accomplished researcher and scholar whose inventions have led to over 50 patents. He has authored over 100 articles and research papers and presented at conferences worldwide for the last 3 decades. He entered IIT Chennai as one of the top rank holders in JEE and went on to finish with academic distinction. Subsequently, he did his doctoral research at the University of Illinois at Urbana-Champaign in computer science. He went on to continue his research at Intel, Qualcomm, IBM, and now finally, he is the Vice President at Reliance Industries, leading research and innovation. We met when we were young in graduate school years of doctoral studies, and it has been a matter of pride to have known him as a lifelong friend. Today, he will now be speaking on quantum computing. Dilip?
Hey, Asif, thanks for the intro. Yeah, it's been fun in this life knowing Asif, and hope I get to know you in future lives as well. For me, Asif has been a wonderful soul. It's been part of my journey in life. So thank you, Asif, for being there. And just want to talk about some work that I have started venturing into personally, just out of interest, and thought I would share some of what I've learned. And I'm still learning, and maybe able to answer some of your questions and not others. But I will plead ignorance when if I don't know. So, one of the things that's going on with regard to the work that I'm doing is that we are deploying like future 4G, 5G, 6G kind of networks. And in that, the infrastructure is getting increasingly virtualized. And I just wanted to give you a context of where the research is coming from. Is the infrastructure is virtualized, everything is executing as microservices and containers or virtual machines. You may have like a cloud data center, an in-network data center, an edge data center, and things like that, and these microservices are executing different tasks. It's not just about the network, but it's also applications and services and things like that. So then there's, as you all know, there's this trend towards disaggregation, things like that, with microservices. And we've started working on AI, ML algorithms and blockchain. And so we can think of quantum-inspired algorithms as well to execute inside these microservices. Some recent work has happened where somebody was trying to create a recommendation engine, but just by designing the algorithm in a slightly different way, as if you're exploring a superposition of states as you go along in your search, but executing it on a classical algorithm, classical computer itself. That itself gives different benefits and improvements in the results that come about. So people worry about when quantum computers will be available and things like that, but maybe we don't have to wait. Maybe we can just write our algorithms quantum inspired. Seeing how physicists and engineers have tried to build quantum computers, and when the computers do have a lot of qubits available, we could also use them. They're already available, but they can probably solve smaller dimensional problems right now. But we don't have to wait, is what I'm saying. We can think quantum in the way we design an algorithm and see if that leads us somewhere. And people are just beginning to do that. So maybe this talk will lead you down that journey. So just getting back into quantum, there's this famous double slit experiment that you would have you'd have seen probably in your 12th grade studying physics and trying to find out what's the distance between the peaks and the that fall on the screen in the back. But you know, when we studied that in high school, we thought of light, a whole bunch of photons going on a screen which had two slits, and then you would get this interference pattern. So we used to think like these were waves and they were interfering with each other, and so you get these peaks and troughs and all of that. And but the interesting thing is, the funny thing is, if you slow this down and just, you know, you're sending 100 photons, maybe you slow it down to 50 photons, 10 photons, 5 photons, finally bring it down to a single photon that you're throwing at the slit, but you send a photon at a time, and then you observe the pattern over time, you'll still see this interference pattern, which sounds crazy, isn't it? I mean, in the sense that a single photon had the knowledge about the probabilities in the system to actually work with the future photons to actually produce this interference pattern. So, so what's happening is that this single photon exhibits characteristics not only of a particle but also of a wave, and as you know, probabilities associated with which path it will take to finally end up on the screen. And then when you take a collection of photons, you actually get this. So so it's neither a wave nor a particle actually, but you know, it's the you define it as if it's a wave function with a certain behavior, and the different paths that it can take are all in superposition, and at some point just before observation it ends up taking one of the paths, or at the time of observation on the screen. So people have even tried to peek at the at the other side of the slit to see, hey, can I see what's happening to the photon? But the moment you observe it, you're forcing it to take a decision. So it's really funny, but in quantum realm, the qubit or these quantum particles stay in a superposition of states until you mess with them, and you know, you try to observe them, and then they collapse to one of the states. And so you never know what it was what state the photon was in, or what superposition of states, what probabilities they were in. When you make a measurement, you just get one of the states. So, and then, you know, it's deterministic after that. So this, so this double slit experiment had this interference pattern with this constructive and destructive interference, but you know, still get it even if it's a single photon. And so each particle is in a superposition of states, and the measurement collapses the state. And I'll just introduce a few equations, but we'll quickly go to the quantum computing part. But some of the properties are that, you know, like a photon has energy. We say h nu or hf, right? But there's also this reduced Planck's constant. That's another way of writing it, as h cross omega, and which is h by 2 pi. And similarly with the de Broglie's equation, you would have seen lambda equals h by p, but you can write p as h cross k. So where k is called the wave number, 2 pi by lambda. So there are two different ways of writing the equations. If you introduce the 2 pi and you use the reduced Planck's constant. And so typically you use k and you use omega rather than f or and lambda. And then the energy, let's say, is p square by 2m for a quantum particle. The phase velocity, if you look at, would be omega by k. And then if you just take the energy divided by the momentum. This omega by k, you can multiply this h cross on the numerator and denominator, and you get E by P. But then it looks like it's V by 2. But actually what's happening is it's not just a single particle, it's a group. It's a packet that is constructed by a superposition of waves, which has a group velocity, which is given by this d omega by dk. When you do that and you still multiply these h's, you get dE by dP, and then the 2 cancels out, and you get the speed. So that there is actually, the particle is moving as a wave packet, as a combination of, as a superposition. And this, if you think of, like, it may have some characteristic lambda or wavelength, or this wave number. This omega is typically a function of that. You know the frequency, you can find the frequency once you know the speed and wavelength, right? So, so the omega is a function of k, where k itself is not discrete, like it can be a continuous function. Think of it like a Gaussian function with a very sharp peak, and that's the group of waves, that's actually moving in this case. And so I'll skip all this, but it turns out that so Asif didn't want me to throw you too much of equations from this side, but at the end of it, it turns out that they all obey what are called Schrodinger's equations. This is for a free particle. There's another equation in the presence of a field, and so on. So, but the interesting thing is that this kind of a differential equation is linear, in the sense that if you have psi, let's say you have psi 1, and then you have psi 2, you can linearly combine this so that you can think of linear superposition or weighted superpositions of these wave functions. So, so when we talk about quantum computing, what's really happening is all these physical phenomena are happening in the background, and we just abstract it away with this notation. And then we forget that, hey, all of this integrals and differentials and all those things are going on out there. So now, and the thing is, you don't have to really worry about it. I mean, the physicists will take care of all of the physics behind it. What happens is that a whole bunch of different types of operations can be performed on what are called quantum bits. And you don't have to worry about how it's getting done inside the quantum computer. It's just like when you do digital design and you have NAND gates or NOR gates and things like that, you can combine these gates any way you like to realize some digital function. In the quantum realm also, you have a whole bunch of functions that can be realized, and all that they do is they work on the bits, and the operations are matrix operations on those bits. And when you do some computation, when you go through a sequence of gates, you're just multiplying one matrix after another. So and the end result is the product of all the matrices, from right to left. The leftmost is the most recent operation that you perform in the qubits. So so now you have available with you a library of gates that you will work with to actually operate on qubits and try to do some fun stuff. So I'll try to explain how a couple of things like quantum search and quantum optimization get done, but just some preliminaries about how you work with these qubits right now. So this wave function, let's say you have, we said, the particle, the state of the particle is not known until you observe it. And when you observe it collapses, it will collapse to either 0 or 1. So let's say there's a particle with two states, and describe these two states as a 0 and 1. This can be like spin up or spin down and things like that. And there could be a probability associated with each of these states. And now these are the psi, this notation, a vertical sign, followed by this wave function, followed by the right arrow. That's the description for the wave function. Now you write that as a summation of this possible states that you can take, 0 or 1, and these are called amplitudes. What's standing in front of the 0 state and the 1 state. The probabilities are the squares of the amplitudes when they're real, but you actually take the complex conjugate and then multiply that to actually get it. These amplitudes can actually be complex. The notion for complex is basically that there can be a phase associated with the rotation if it is not real. So, but it's just that phase is getting captured as a complex representation. So what you have is there are two states. There are probabilities associated with the states such that alpha 1 square plus alpha 2 square equals 1. Think of them as real for now, and just that what you have here is the square root of the probabilities. So if they were equally likely, the probabilities would be half and half. So what would alpha 1 and alpha 2 be? Can anyone tell me? What would be the amplitude? Pardon?
The probabilities are half, right? Alpha 1 and alpha 2.
Alpha 1 square and alpha 2 square are the probabilities.
Mm-hmm.
So alpha 1 and alpha 2 will be? So alpha 1 square is half. Alpha 2 square is half.
Is it 0.707?
Yeah, right. 1 over root 2, 1 over root 2. And you will see that, it'll continuously getting used. So don't, when you see that, don't get scared. Hey, where's this square root of 2 coming from? Stuff like that. It just, and we'll see what this means. Why in just a bit. Why there is a square and things like that. It actually relates to energy. Just a bit. So so what happens is that typically light as it's traversing, it's a transverse electromagnetic wave. The direction of the electric field is called the polarization of the photon. The electric field is oscillating in one direction. The magnetic field is oscillating in a perpendicular direction, and the wave is propagating perpendicular to both of them, E cross H. So and the direction of the electric field is called the polarization. And if a photon arrives at a polarizer, and magnitude is A at an angle alpha, then A cos alpha is the amplitude that is transmitted through the polarizer. And then the thing that's perpendicular to it will be filtered out. So the energy of the wave is proportional to the square of the amplitude, and hence proportional to cos square alpha. So cos square alpha is a fraction of energy that gets transmitted past the polarizer. So think of the probability as relating to energy, right? You have amplitudes, and but the probability relates to the energy in the system. So there's a probability cos square alpha for the photons to go through, depending on the polarization and the direction of input. And so what you say is before it hits the polarizer, there's a component, say along X that is going to get transmitted. That component has a value cos alpha. There's a component Y that's perpendicular to it that's going to get filtered out. So it's in a superposition of states with amplitudes cos alpha and sin alpha. Once it gets through the polarizer, the state is just this photon X, right? It's just more has a component only in this x direction. So there's now this amplitude is 1. There is no more of this y to thing. So it's at this point. So what happened was that this cos square alpha was effectively how much energy went through. If you put through a whole bunch of photons to the polarizer, the total energy coming out will be cos square alpha of the input energy. So that's where you can start thinking of what these probabilities are, the relative energies in the system. Now, and as you said, these quantum particles in a superposition of states, but if you try to observe it, the moment you observe it, the state of the particle collapses. It will collapse to either 0 or 1. But it depends on the probability. So if the probabilities for, say, state 0 is higher than the probability for state 1, then there's a possibility that when the collapse happens, it will actually go to state 0 instead of state 1. And vice versa, if one has a higher probability. And that is what is used in, say, a quantum search algorithm, where what you try to do is you try to manipulate with these probabilities such that when you try to collapse, you end up with the answer to the problem, because the answer to the problem has now achieved a higher probability through the manipulation through quantum gates in the system. And we'll see how that is done. You know, the moment you observe, you have you've completely lost information about the probabilities that that particular quantum particle had. All you know is what state it took. So it's possible that 0 was higher probability. When you measure, you get a 1. So you have no knowledge that 0 was indeed a higher probability at that point in time for that particular photon. So and because of this, you know, there's also this thing called no cloning theorem. That is that you know, you can clone a digital bit. You can copy one you know, a bit with it's either a 1 or 0 to some other place in memory. But a quantum particle cannot be copied because we don't know the probabilities that it has. So that's so you have to live with that. You have to live with all these idiosyncrasies and still try to you know, utilize.
Hey, this is Avijit. Can we ask question in between or towards the end?
Yeah, go ahead, please. Please ask.
Yeah, just one question. In the previous slide, you don't have to go back. You said that we don't know anything about the states. We just know once we observe whatever the state it is, that's what we know. We manipulate it by transforming. So how do you transform if you don't observe?
So I'll come to that
Okay.
a little later. But you keep the qubits in the quantum states and actually apply what, say, if you can do a Hadamard gate, which is actually trying to entangle qubits, which effectively is implemented by putting it through a polarizer, beam splitter, and then out comes an entangled set of qubits, which you can work with. But the probabilities get carried through in the process. And we'll see how that happens very quickly.
Okay. Yeah, I think it will be clear. Thank you.
Yeah. So, the typical convention is 0 is represented as a column basis 1, 0, and 1 is represented by the column basis 0, 1. And then the wave function as a superposition is represented as alpha 1, 1, 0 and alpha 2, 0, 1. So actually just leave it like this rather than this. And then if the two states are equiprobable, like we just discussed, it could be 1 over root 2 and 1 over root 2. That could be minus 1 over root 2 and 1 over root 2. There can be an I also in this out here. So so we can have another quantum particle B, which can be in similarly in superposition of states, but maybe the probabilities are different. such that the sum of the probabilities is 1. Now, when you work with multiple qubits, you have to think of the combined state of those qubits. If they're not entangled, then all possibilities are available, 0, 0, 0, 1, 1, 0, 1, 1. And so you do, you represent that as a tensor product. But don't get tense about the tensor. We'll see exactly what it is in just a bit. But if you try to, expand it out, you can see that you get alpha 1, beta 1, and then 0, 0, alpha 1, beta 2, and 0, 1, alpha 2, beta 1, 1, 0, alpha 2, beta 2, 1, 1. Now, this looks a little scary, but we actually end up write it more simpler, and then now it's getting less scary, right? So 0, you write this guy as just 0, 0, 0, 1, 1, 0. But now, if you write that, so the two particles, this is the combined state, alpha 1, beta 1, 0, 0, 0, 1. And if you take the squares of all of these things and you add them all up, you'll find that some of the probabilities are still 1. Can somebody tell me now, if you have these 4 states, what would be the, if they're all equally likely, what would be the numbers sitting in front here?
Half, is it?
Yeah, half, yes, half, because half square is 1/4, 1/4 plus 1/4 plus 1/4 plus 1/4 is 1. Yeah. So instead of 1 over square root of 2's, you have halves. So 2 bits are more fun. You don't have the square roots anymore. So, okay, so this is what a tensor product looks like. Okay, all you do is you take this column vector and then this column vector, and so this is 0 and 1. But let's see 1 applied to 0 kind of thing, so then the vectors look different. So this 0 we said is 1, 0, right? So you keep repeatedly applying the bits associated with this column vector on the other column vector for 0. So this is 0, this is 0, and then 1 was 0, 1, right? So 0 is applied to 1, 0, and 1 is applied to 1, 0. And you get a 4-dimensional column vector, which is 0, 0, 1, 0. And similarly, say 1, 1, 0, 1 is applied to 0, 1 up here and down here, and you get 0, 0, 0. And similarly, 0 acting on 0, you get 1, 0, 0, 0. So you get all 4 possibilities. This is like one hot encoding, right? So you get 1, 1, 0, 0, 0 for 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Now, what if you had a third qubit? Can somebody tell me what these column vectors would look like? If you repeatedly apply, what do we have to do? You have to take each one of these guys, and then let's say you have to apply it to, it acts on a 1. Then what is the length of the column vector? Each of these entries in this column vector is acting on this 2-bit column vector. So how long will it be?
8.
If you have to apply it to another qubit?
Is it 8?
Yeah, 8, yes. So, and then you can build it. So that's called a 3-qubit register. And then you can grow any number of qubits. So, 0, 0, 1 is like this. And then these are the 4 possibilities, 0, 0, 2 qubits. There's another notation which is called the inner product, which is basically the mirror version. This is called a get and this is called a bra. And so the inner product is called a bracket operation. And it's actually obtained by using the conjugate transpose. And if it's real, you just take the transpose and just multiply. And so it's like a dot product kind of thing, right? So you just and these were our column vectors, right? The kets were our column vectors. So if you take a transpose, this becomes a row vector. So the row vector acts on a column vector and gives you a number, and that's called the inner product. So we will see the usage of this a little later. So then there are unitary transformations that you, like I said, when you do quantum computations, you're applying unitary matrices. So to transform them, and this basically entangles them, helps in entangling. So we'll see how we actually entangle a little later. But so a unitary matrix has a property that if you apply it to itself, you get an identity matrix. So you apply H to itself, you get, say H is this matrix, which is trying to, the first row is just copying over, it's not changing, but this one is flipping the second component in the column. So, so what does it do? We'll see a geometrical representation of it, but you can see that if you multiply this matrix twice, you end up getting the identity. Right? So it's unitary. And when H is applied to 0, so you have this H matrix and you apply it to 0, you get 1 over square root of 2, 1, 1. So this is like at 45 degrees, right? And and this one is 1 minus 1, so this is sort of like a minus 1. So this output, when it's applied to 1, 0, getting transformed to this, is also called this plus state. It's also called a minus state. These are also called Bell states. So, but geometrically, you can see what's going on. 1, 0 is 0, right? Let's draw 0 on, say, what's the x-axis. It's rotating to 45 degrees. So I say, hey, is it a 45-degree rotation? But then look at 1. 1 is, let's say, up here, pointing towards the y-axis. But if you rotate it and have 1 minus 1 with 1 over square root of 2, it's actually pointing downwards here at a minus 45-degree angle. So, so it's not just a rotation by 45 degrees. This guy's rotating by 45, but this is 135. And this is anti-clockwise, that's clockwise. So is there another way to look at it? You can draw a line at 22.5 degrees and say, I'm going to reflect at that. So you reflect along pi by 8. And then, yeah, hey, this guy goes here, that guy goes there. So this is one interpretation. This is a reflection transform at the angle pi by 8. But there's another way of looking at it, which is first rotate clockwise by 45 degrees and then reflect around 0. Okay. So, oh, by the way, if we go back here, we said these matrices are unitary, right? So if you apply to itself, you should get back what you got. So if you define this as rotation around pi by 8, this goes reflection around pi by 8. Then this goes here, and if you reflect it back, it just comes back here. So this guy goes here, and then you reflect back, it just goes back there, right? So all that's, so you can see that when you apply it a second time, you just get back what you started. So let's see if that works here also in this thing. What happens is here, the other interpretation is let's rotate 45 degrees clockwise, and then reflect it around 0. So then it goes here. This is fine, right? That's this guy. What about 0, 1, 1? Rotate it clockwise by 45 degrees, it reaches this here, and then you rotate it around 0, so it goes down here. So, so yeah, you can rotate by clockwise and then reflect. What if you reverse the operation? If this guy, so now we have this, right, as the result of applying the matrix once. If you rotate clockwise by 45 degrees, you end up at 0. And then you reflect around 0, you stay where you are. What about this guy? You rotate clockwise by 45 degrees, you end up here. And then you reflect, and then you end up back there. So you still, both interpretations get you the same answer. So there, but here what you would say is you would apply a rotation matrix followed by a reflection matrix. But this rotation matrix is for pi by 4. Whereas the other one would just say reflect with respect to the pi by 8 direction. Right? So effectively, all that's happening is these are matrix transformations that are happening, and and then you apply them in sequence. There are other types of gates. There's an identity. There's an identity gate. This is a polymatrix. These are polymatrices. Asif can tell you a lot about what all of these mean in physics, but relate to spins and all of that stuff. But for us, it's an abstraction that it's just a matrix that you multiply. But this one, you can see, just flips the bits. So it's also called a NOT gate. This polymatrix. And this is another gate called a C0 gate, which flips a target bit if a control bit is a 1. So, and it's very useful, extremely useful for entanglement. So see what it does. So you have this, let's say you have 4 different probabilities, 0, 0, 0, 1, 1, 0, 1, 1. Now, let's call the first bit a control bit. So if the control bit is a 1, then it's going to flip, right? So it's not going to change. If this guy is a control bit, it's not. If it's 0, it's not going to change. So this remains unchanged. This remains unchanged. But here the control bit is a 1. So the second bit flips to a 1. And here it's a 1. So the second bit flips to a 0. So it selectively flips the second bit if the first bit is a 1. That's an interesting property that this gate has. And in general, you can have k qubits. And so 2 raised to k possible states, like you said, when you had 3 qubits, we had 8 possibilities and so on. So, and then you have each of those states can be are all possibilities, and then there can be amplitudes associated with the states. And so when you're trying to search for something and you're trying to find something which is highly probable, basically, you're trying to find the one which has the highest amplitude. So this is a single qubit register, right? This is a 2 qubit register, right? This is a 3 qubit register, right? And so on, right? So you don't have to worry about tensor products anymore. It's all just it all looks like this. So now comes a very interesting thing called quantum entanglement, which is a phenomenon where you actually take 2 photons, but if they could be directly entangled or inversely entangled, in the sense if you make a measurement on one of the entangled photons, then you can observe the state of the other, and if you observe the state of the other photon, it will end up, if they're directly entangled, it will end up being the same. So observation of any one of them collapses the state, but it also immediately collapses the state of the other one, even if you didn't observe it. So you can observe it, go in and observe it at any point later in time, and you'll find that it is what it would have collapsed to. So you entangle them, but we could be inversely entangled as well. But the quantum entangled state would be represented like this. Like if it's directly entangled, if one is 0, the other is a 0. If one is a 1, the other is a 1. And then you would have 1 over square root of 2. It's coming back to haunt us. So these are the Bell states, but it's not decomposable anymore. Like you can't write it as the state for the first qubit tensor product with all possibilities of the second qubit. Now that you only have 0, 0, and 0, 1 as possibilities, so you can't decompose it individually, and that's why it's entangled. You could have inverse entanglement also, 0, 1, and 1, 0, and so on. And this is possible, like when you generate particles of opposite spins, and so the entanglement is opposite correlation. So if you observe 1 and you see a 0, that means the other one is collapsing into 1 at the same time. And this they have shown happening across distances or 130 kilometers and so on Earth. They've shown it working in space and things like that, to ground, to Earth. but distance is sometimes a problem, I believe, to propagate the light and to actually receive it on the other end. And then you can have multiple entangled photons as well. So if there are 4 qubits that entangle directly, write it like this. Right? But you can have a hybrid combination of this entanglement for multiple qubits. So how do you create an entangled qubit? You apply the Hadamard first. Right? Hadamard is the reflection that we just talked about. So when you apply the Hadamard, let's say you have this. You have 2 qubits and you apply the Hadamard. What's happening, let's say, is you apply it to only one of the qubits. So let's say we apply it to the first qubit, right? So then the 0 is going to expand into the 45-degree direction, right? So it'll be 1 over root 2 0 and 1 over.
Now you're fine. We can hear.
Okay. Yeah. So you apply the this Hadamard transformation to one of the qubits, and then essentially expanding one of the bits in the 45-degree direction, and you keep doing that, but holding the other bit as it is. So when you do that, the ones became like had the minus 1 over root 2s, and then if these probabilities are all equal, the minuses cancel, and then you're just left with, say, this 1 over the zeros combining and the 1 zeros combining, but the 0 1 is cancelling with another instance of the 0 1 if these gamma 1 equals gamma 2 and then gamma 4 equals gamma 3. And so you end up with this kind of a result. But you really, when we wanted entanglement, we wanted this to be a 1. So when you do that, to do that, you apply the C0 gate. So C0 gate says, if the control bit is a 1, I'm going to flip. So this is a control bit, and when it is a 1, it's going to flip. So you apply the C0 to this system, and then you get this. So applying the Hadamard followed by the C0 creates an entangled state. And then that is used a lot in quantum processing. So you apply these kinds of transformations repeatedly, and the probabilities get refined during processing, and the higher probability state could become more and more likely and provide a good solution. And you can also do hybrid solutions. You can set up the problem for the quantum processor, let it do some stuff, make a measurement, then you can set up a different modified problem for the quantum processor, and then keep doing this in an iterative fashion. And there is a famous algorithm called Shor's algorithm for factorization, which tries to find the period of a function in the first part classically, and then applies what's called a quantum Fourier transform, which utilizes the Hadamard gates multiple times, followed by additional transformations, and to get speed up in the quantum realm. So you can look at the Wikipedia page for it. You'll see a circuit structure, and you'll see a whole bunch of horizontal lines. Each horizontal line is a qubit, and then you can put them through gates and things like that, and out comes the final answer. So with quantum search, you want to work on these qubits, but you want to find, you want to target the search in a particular direction. And the key technique is called amplitude magnification. You want to amplify what could be more important. So I'm applying this currently to, say, wireless networking. And so if I want to give a node that has to transmit more importance, I'll apply this transformation, this what's called an oracle, that tries to focus on that particular state that's more important. And then we do a reflection. So So this algorithm is called Grover's algorithm. Let's say you have n items, with each one has the state xi, and we are searching for one of the items, I equals k. So we can create a quantum state, which is superposition of states of all of these n items, and you get this kind of an equation. So initially, all these states are equally likely, and so when the amplitudes will be 1 over square root of n, right? Because the probabilities are 1 over n, so the amplitudes are 1 over square root of n. So now, what you're searching for is inside the wave function with an amplitude of 1 over square root of n. Now, what you do is you apply what's called an oracle function such that it changes the sign of the amplitude for this and leaving the other ones unchanged. So all the other states remain with probability 1 over square root of n, but this particular xk has an amplitude now of minus 1 over square root of n. Then what you do is you reflect with respect to this psi, and this results in an enhanced amplitude for xk. And then you keep doing this again and again. You'll start improving the probabilities for this while the other probabilities reduce, and we'll see exactly why that happens. First, let's understand what's reflection. The reflection is defined as this equation, and let's see what happens if you psi is 1, 0 and you try to apply it to itself. When you do this, this is the ket and this is the bra. When you apply it one next to the other, you get 1, 0, 0, 0, right? And you do twice that minus I, so twice this matrix minus the identity matrix, and you get 1, 0, 0, minus 1. So you apply this, let's say, on 1, 0, and you'll still get 1, 0 because 0 minus 1 acting on 1, 0 will give you a 0. And 1, 0 acting on a 1, 0 gives you a 1, 0. So under this reflection, based on this psi, 1, 0 remains unchanged. But if you apply it to 0, 1, right, then 0, 1 reflects and becomes 0, minus 1. So if 0, 1 was pointing in the positive y direction, now it will point in the negative y direction. But if this guy 1, 0 is pointing in the positive x direction, it remains where it is. So you can see that the reflection transform. When you say reflection by psi, with respect to psi, if you apply it to psi, it shouldn't change, right? Like when you saw earlier, we were reflecting along with respect to the x-axis, and if you're already on the x-axis, you don't shift. Right? So that's what's happening. You can see if you change psi to 0, 1, the same thing happens. When you do the psi, this get with the bra, you end up getting minus 1, 0. So when you apply minus 1, 0 to 0, 1, to minus 1, 0 to 1, 0, you get a minus 1, 0. But when you apply it to a 0, 1, it remains unchanged. So you can see that, now 1 doesn't change, but 0 is getting reflected with respect to 1. In general, now let's say you apply this reflection transform to psi itself. What happens is you have this bracket here, but this is a unitary matrix. It's equal to 1, and then you get 2 psi minus psi equals psi. So applying the reflection on itself doesn't change it. But what if it's orthogonal? What if there's a wave function that's orthogonal to this, and you apply it? Then you see that this inner product is 0, and then you get and you're applying this on phi, and so you get this times phi, and then identity times phi. But this inner product is 0, so you get just minus phi. So phi gets reflected, just like we saw 1, 0 getting reflected earlier. But now this is more general. Psi could be any direction. And now for any general phi that you act upon, now you look at this reflection transform. What is it doing? There's an inner product here. This psi acting on phi minus phi. What is this doing? This is making phi go negative, the totally opposite direction. But because we want the reflection to be with respect to psi, we're having this additional term. What is this? This is the component of phi in the direction of psi, right? So, and you add that twice, so you reinforce it back because you made it negative. Let's say you had a cos theta, you made it minus cos theta, and then you added 2 cos theta, and so it becomes plus cos theta back again, right? So what happens is when you do this, the component of phi along psi remains unchanged. But the other portion, the sign, has become negative. And so you've reflected the component of phi that's orthogonal to psi. So thus, you know, this reflection transform will reflect with respect to psi, anything that you apply it to. And like I said, when you're applying these matrices on these qubits or a transformed version of these qubits. So now let's go back to what we said. In the quantum search, we first will do this transformation where, you know, you apply the oracle function, which flips only this guy to -1/10. And then, you know, you do a reflection with respect to psi. But you know now what reflection means. But what does the math look like? So the oracle transform, what does it do? It's making xk -1/10, right? So so that can be written as subtract, you know, because you had psi had 1/10, and when you subtract -2/10, then xk's component is -1/10, but all the others are still remain as +1/10, right? So this, you can, the oracle transformation can be represented as this, and then the reflection transform is like this, and we already saw what reflection happening on psi is, and it just produces psi, right? 2 psi minus psi, these are the two terms coming from that.
Hey, Dilip.
But then there's also the this reflection acting on this part, -2/10 xk. And when you do that, there is this psi acting on xk, and you get a 1/10. And there's a 2/10 acting on this xk. When you do the math, you finally end up with a -1/1 -4/n psi, and then 2/10 xk. Where did this -4/n come from? This is because psi xk is 1/10, and then you already had another √10, and then there was this -2. So all of this give you a -4 divided by n. Now psi still contains xk. So there is a 1/10 times 4. So the xk is amplitude 1 -4/n into 1/10 plus 2/10. And if you look at this, this is approximately 3 divided by √10. But the other states now have reduced in amplitude. They used to be 1/10, now it's 1 -4/n into 1/10. So xk has undergone amplitude magnification. Right? And then if you kind of repeat this multiple times, then you're very likely to select something with a very high probability. So the way I'm doing this, say for network access, is if some node has higher favorability, I would say the link conditions are better, then you apply the oracle transform for that entity so that its probability gets improved. But if somebody else's link condition improves, then you apply the oracle for that one, so that you keep shuffling around the probabilities, and then you can pick any one of them to actually transfer. So, so the process is applying this oracle to actually flip, you know, the probability for one of them, and then do the reflection. And so you're doing amplitude magnification, and that helps in finding what you want to find. So that's how searches are done. And then, so these kinds of things are basically done with a sequence of gates. And typically these are called, the quantum computers that IBM, Intel, Google all put out. They have, you know, a few tens of qubits. Now there's another class of quantum computers called annealing-based quantum computers, which D-Wave works on. And those are slightly different. There you don't have, you don't synthesize any, don't have the ability to synthesize any kind of sequence of gates and things like that, which the Intel, IBM, quantum computers do. But what you have is they are in a matrix, just like, you know, a GPU kind of thing. You know, all these processors are like all in a mesh, closely connected, and then you can operate with your neighbors and things like that. So it's a lattice of 2048 superconducting devices, and it's chilled close to absolute zero. And you model the problem such that you search for the lowest energy point in your landscape. So, so now what you do is you're trying to find this lowest energy state. You're searching for something in that space, and you're allowing all of these bits to interact with each other, but you allow the neighbors to interact and so on. So it's sort of a mesh where all these qubits are interacting with their respective neighbors. And then you evolve it over time to find the answer. So, and you have what are called quantum processing units and quantum machine instructions. And you can submit these quantum machine instructions to the quantum processing units, and then they evolve the system. One of the examples that we talk about is quadratic unconstrained binary optimization. We're trying to find the states of all of the qubits such that the energy is minimized. Okay. So you have these weights corresponding to all of these variables, and you have a function, and you want to assign values to these states such that this function has the lowest energy. So here's an example. So there are 4 nodes, and they could be self loops. So if you say, I'll pick 0, then the energy goes up by 3.4. You want to reduce the energy. So you'll say, hey, I'm not going to pick 0 because, you know, the coefficient in front of it is 3.4. But I'll pick 3. Hey, that's negative. So let me pick that. So let me drop all of them and let me just pick this. Okay, maybe that's my lowest energy state. I just have third bit assigned to 1 and 0, 0, 0. But no, hey, there is also coupling between these bits, like 0 and 1 are coupled, 0 and 2 are coupled, and there's energy associated with that. But we are trying to minimize the energy, right? So maybe we pick the ones that are negative. So we could say, let's pick 2 also, because 2 and 3 are negatively coupled. Hey, but if you pick 2, then, okay, I'm increasing, reducing the energy by minus 3.22, but let me see if, you know, adding 2 makes it worse. No, actually fine, I'm fine, because 2 is 2.1 and the coupling is more negative. So it's okay to add 2, but is it okay to add 1? Look, 1 is, if you add 1, it has a self coupling of 4.5, and then combined with 2 is another 4.5, and 1 with 3 is another 4.5. You would just increase the energy a lot, so you wouldn't bother to add 1. What about 0? You add 0. Zero's couplings are also highly positive. There's a negative part, but there are more positive parts that override the negative. So at the end, you'll say, okay, I think my final assignment is 2 gets a 1, 3 gets a 1, and 0 and 1 gets 0, 0. That's what the D-wave solves, and finds the final energy is minus 3.52, which is minus 2.4 plus 2.1. So you're at minus 0.3 when you just do 2 and 3. And then you take the coupling between 2 and 3 is minus 3.22. So that's minus 3.52. That's the energy of the system.
Hey, Dilip, can I ask a question?
Yeah.
I have some basic question, very basic questions. So what is qubit? Like very layman's term, if you could explain me what is qubit.
So essentially, think of that photon, right? Or in a superposition of states, and you're allowing it to be in a superposition of states. You saw the Hadamard gate, right? Which actually takes it into an entangled kind of form. So it rotates it. And so, you know, if you had measured it and say it was actually in a state 0, by putting it through the Hadamard gate, you actually end up in a superposition of states. That you can manipulate with. So, so what you do is you end up utilizing the superposition let's say you have multiple photons, you have them interacting with each other. They are all in a state of superposition. You allow them to continue interacting with each other in the quantum realm. Then you make a measurement. If you do make a measurement, you can still, apply Hadamard gates and then things like that, and go back to kind of cross-coupled states and things like that to actually work with these qubits again in the quantum realm. But essentially, a qubit is saying, hey, I may be either in state 0 or state 1, but and these are the probabilities that I may be in. And so in software, if you try to simulate this, what you will say is, I have a head or a tail, but I have probabilities associated with the head and the tail. And you'll represent, let's say, a JSON object with head and tail and the probabilities associated with them. And that you will call as a qubit.
I see.
Right?
So
in software, you would have just said head or tail. But if you try to write a qubit, you'll say, I have two possibilities for it, head and tail, and these are the amplitudes for it. And the squares of them are the probabilities. So then you just define that object. And then when you try to implement a quantum algorithm, you manipulate with these quantum data structures repeatedly. And you can apply these matrices and things like that. And then you can make a measurement, all in software. You can just do this in classically on a classical computer, but just represent them in this form.
I see. And so quantum search is basically search for that qubit state, any of the qubit state, right?
You're trying to search for some particular item, something that's higher, more important to you, or you're trying to find something that's more highly probable. But you essentially, you have to apply an oracle transform towards that. So you have to keep applying the oracle transform to a system to keep trying, maybe different variations, to different items to see if which ones are important, and then amplify them. So, but your external input may say, hey, this is what I want to amplify. For example, like I was saying, what I'm trying to do with network access is, I want to allow access to a network to a node which has a better link condition. So when I find that, then I amplify. I work with a quantum state, but I amplify the state of that particular node because it has a higher link condition. So that if I make a measurement, more likely than not, I will pick that particular node and allow it to transmit.
Got it.
So, yeah.
So what is the oracle function or oracle transform if we, other than, can you try to define it other than non-mathematical terms? Like, I mean, the mathematical.
So the oracle tries to differentiate that particular state, that minus xk.
Mm-hmm.
Xk became minus xk, right? So when you try to do this reflection with respect to in a particular direction, because all the others did not change, when you reflect, they will all go somewhere. But the one that is minus actually flips back with a stronger, force and reinforces itself in its original direction, and therefore it undergoes an amplitude magnification. So you flip it, and then you reflect, and then it ends up having a stronger amplitude, whereas the others, go down in amplitude.
Got it.
After the reflection.
Yeah, that helps understand more. Thank you very much.
So, yeah. So I'm almost to the end. So there was two things that the oracle followed by the reflection. Well, yeah, here one more example here. If we add one more qubit to this system, again, you'll see that it decides to do 1 0 1 1 1, and you can work through the math. It basically doesn't allow 1 4 to go on, but everything else, if you add up, so 1 is rejected, right? So then you add this and this, you'll get plus 0.7, right? And you've rejected a 1, right? Bit 1 is rejected. So take 3.4 minus 2, combine that with this guy, this, and this, you'll end up having minus 18.12. So adding up all of these guys, getting you minus 18.82, and then this guy will give you plus 0.7. So you end up as this is the lowest energy of the system. So, but note that this kind of computer is not what we were talking about earlier. It's only allowing some interactions to progress between qubits locally, because it's like a mesh of qubits that are interacting with each other. But you can, change the weights of the correlations between these qubits and then allow it to converge. And where is it useful? For example, they try to do map coloring with this, or to have to figure out a solution to color different regions by assignment of states to with respect to a color for every region in the map and things like that. And then it settles down to something that doesn't have any conflict or minimal conflict and so on. So, but this is more like if you've heard of annealing and things like that, optimization. This is an approximate solution. So what D-Wave tries to do is not like a perfect classical algorithm. The IBM, Intel, Google computers try to do those classical things. You have a fixed algorithm, you know exactly what you get. Here, it could be an approximate thing, and you let it settle down to some minimum energy, and you take that as your answer. You go with it.
Is this, so Dilip, this is Abhijit. Is this something like what we do in like machine learning, where we try to, reduce the error or something like that to a certain degree of, accuracy?
Yeah, you can think of it that way. But then, yeah, you have to have knowledge of correlation. So they think of it somewhat like a clustering problem, trying to partition, and you're trying to, things that are getting strengthened are belonging to the same cluster, and things that that are not strengthening, things that are weakening go to the opposite cluster, kind of thing. So it's trying to create a partitioning and then an allocation for the problem. So if you have an exact algorithm, you will go with like the IBM, Intel, Google kind of quantum computers and build a sequence of gates, and and you write it as a sequence of matrices from left to right. The leftmost will be the last matrix operation that you performed. Whereas with the D-Wave kind of thing, you're trying to kind of find a solution to a problem by mapping it to this kind of quadratic optimization. So these energy functions are called Hamiltonians also, and you're trying to find the minimum energy state of the system. And so it comes from physics, but then you translate that to an actual problem in computing, and then let the quantum computer do the physics and give you the answer, right? For you. So these are some books that are useful. The second one is probably the most useful for, and you can actually get a free PDF online. It's the most celebrated book in this area, Nielsen and Schwann, Quantum Computation and Quantum Information. The first and third are more physics related for those who are curious about, how Schrodinger's equations work and things like that, if you're interested. And there are a lot of Wikipedia and online lectures from different universities, MIT, UC Berkeley, and so on. And then D-Wave also has some documentation, because it does a slightly different kind of quantum computing, more approximate quantum computing. So that may be interesting as well. And for me, I see this as part of a bigger scheme of things where we may have AI, ML, IoT, 5G, and things, blockchain, and so on. And 5G can allocate resources in networks. IoT systems can monitor and provide triggers for processing. You can have blockchain systems executing smart contracts, recording events, but you can also have quantum-inspired algorithms as well, executing in virtualized infrastructure. So that's what's driving me to kind of, because I have to kind of look at future technology as well. So I'm trying to see how to integrate quantum inspired processing as well. So yeah, I was just walking you through my own journey in this, what I've been trying to learn. Hopefully I was able to share something useful. If you have any questions.
Dilip, this is Abhijit again. That was great, actually. You know, you kind of very nicely combined both the theoretical and the practical aspect. This was very nice.
Thank you.
Yeah.
So just Dilip, can you hear me?
Yeah. I will.
Yeah. So we are doing like a quantum searches in your example. So you are constantly taking measurement of all the nodes and just doing a quantum search for a best node and trying to route the traffic through that node. Is that the concept?
Oh, what I'm trying to do?
Yeah.
Oh yeah, so I'm trying to apply it to networking, for example. And maybe, you know, all the different nodes are different possibilities. So of who would transmit next. So I have to pick one of the states or to say whom I'm going to pick next to transmit. So I'll try to apply Oracle transforms to you know, when nodes are more favorable in terms of getting access to the network because their link conditions are better. The other thing you could look at if you're talking about routing could be, hey, which path has, you know, is less congested? And you could apply an Oracle transform to that less congested path and make it more favorable and apply a quantum algorithm to select the best route. So you can keep applying it to different types of problems. Yeah.
I see. So this will be, I think, very beneficial for network slicing type use cases, right?
Yeah, definitely. And not only in networks, I mean, so people have started, see, the thing is, you know, we don't have to actually run these things on quantum computers. We might actually, by creating some quantum algorithm, quantum-inspired algorithm, you could evaluate, you know, a superposition of states. But what I think we have to do is not let it just run completely to the end. Because, you know, let's say we create 2 raised to n threads for each of the possibilities and let them evaluate each one of them. Then, you know, you didn't gain anything, right? Because you, instead of, let's say you started with some random initial state to find what the answer is. Let's say you tried all possible initial states and you have threads running all of them concurrently. And then you find which one is the best one. That's like brute force. So what you have to do is you start exploring, but at some point you have to take a call. Okay, I'm going to stop searching along these paths. Just like in a, you know, how a computer plays a chess game, right? It tries to evaluate different things, but it prunes out different paths. So we have to, if you think quantum inspired, you're thinking of a superposition of states, but you start, you know, narrowing down, and then again try to go quantum, and then again come back and narrow down. Eventually, you probably will be picking the one, you'll be finding the one that you're looking for. So, and hopefully by doing that, you will get a faster speed up, even on a classical computer, just by thinking quantum in how we try to solve the problem. And people have tried to apply it to recommendation engines also, trying to explore different possibilities, but creating a data structure which is as if it's a superposition of states exploring different possibilities. What we should do is, you know, pause and then, you know, that hybrid thing of classical versus quantum kind of thing. You should kind of keep doing that. And, you know, when you think of parallel computation, you have this computation versus communication, and, you know, you have this interleaved phases of computation communication. We should, when you do that computation, you do the quantum inspired, and then you have a phase of communication to kind of reconcile your results to try to decide how to focus, your energies on the next stage of computation. And I think if we try to design algorithms that way, maybe we'll get very interesting results, even classically. But once the quantum computers can be used for that, you might get a higher performance as well.
So when you observed, right, you just the wave function collapse and it becomes particle. Then we try to entangle, the particle becomes wave again. Is that the concept? When you try to create
it remains it's neither a wave nor a particle, but you can call it a our Chandar and I had a professor at IIT Madras who would call it a wavicle. So it's but like we said, when it goes through that polarizer, and it's still a wave function coming out in the x direction, right? So it's but it has a definite state associated. But yeah, you're right. And then you can apply the you can create an entangled state, if you like, and things like that after measurement. And so then you go back into the quantum state of superposition of these qubits. You have fun with it, and then again you take a measurement, like you just said. Yeah, and that can be fun. We can try to do some interesting computation.
Yeah. So when you try to create entangle, how are you going to save that information? What kind of data structure you will use to save that entangled, like superposition information?
When we write a computer algorithm, we can actually save it in the sense. It's a data structure in the computer with different probabilities. But in an actual quantum computer, you can't see it.
Nice.
If you make a measurement, it will collapse, right? So actually you have an advantage. If you write a program which is quantum inspired, you actually can see the probabilities because you're evolving the probabilities as you go along, because you have a data structure to represent the entangled state, right? But the actual quantum computer, you're at the mercy of the physics. The probabilities are evolving internally. All you can do is take a measurement and see what it provides as an answer.
Nice. So it's the software level. Okay.
Yeah. So you could do completely in software, then you have access to everything. But when you abstract the quantum computer out, the actual physics part of it out, you don't have access to the actual probabilities associated with states. You know the states that it could be possibly in, but you don't know the probabilities associated. And it will collapse to one of them.
Okay.
Any other questions?
Yeah, so I have one question. So what kind of physical systems you use for making these qubits, like these 2 photon states or 2 quantum states?
Yeah, so they use this superconducting systems, super cooled, to almost 0 degree Kelvin kind of thing. And,
that's for the D wave. That's for the D wave?
Yeah, all the computers are like that. They're operating at very low noise levels. It has to be super cool so that noise is extremely low, so that the probabilities are preserved and things like that. And then you use these polarizers and beam splitters to kind of do this gate transformation, such as the Hadamard gate and things like that. And so it's a lot of superconducting conductivity physics that's going on. And Asif can probably tell you more about how these or how the physics works. But, yeah. But what happens is that, okay, what the physicists will do is they'll say, okay, look, this kind of operation is what you want. I will do it in my quantum computer and this is my result. So, you don't have to worry about it. Like, you saw the quantum machine instruction, right? All you have to say is you have to issue the instruction, and internally the physics will execute that instruction on these photons.
Okay. Thank you. Thank you for the nice talk.
Yeah, one thing to add from a physicist perspective, See, the quantum computing theory, like Dilip explained, is ahead of the physics. It's very well developed. There are remarkable things that are arising. It's becoming popular. You can actually use languages to do quantum computing, at least simulating it on ordinary computers. Physics will take a little bit of a time to catch up. Just 2-3 days ago, on June 25th, we had a fundamental milestone in this. I don't know, some of you may have heard about the CubeSat. There's a satellite, and on that satellite, for the first time, quantum entanglement was actually observed, and it's quite exciting actually for the physicist community.
Oh, okay. I didn't know that.
Yes.
Thanks.
Dilip, just one last question.
Sorry.
Yeah, is how heavy of computation it is, right? Like on, let's say, node, like you need a lot of computing power or software?
Yeah, actually these systems apparently take a lot of energy, but hopefully they can solve a high dimensional problem much faster, and therefore it would be worth it, to execute on these computers.
So in terms of 5G network, for example, can you implement it at the edge device, edge nodes as well, not at the edge device?
Oh, no. Actually, nowhere close to that, right? Okay. Because this will be some super cool thing sitting in some specialized location somewhere. So what you have to do is you have to send you have to set up the problem, send it to the quantum computer, and ask it to give an answer.
It is almost like the olden days we used to put punch cards in the mainframes like that.
Oh, wow.
Now, there'll be a bit of latency to access this thing, so it better solve this higher dimensional problem for you. But there is this part, but there's also this part of being quantum resistant, which is if you do all your computation, just be quantum resistant. So a quantum computer could do some prime factorization and break your cryptography. And so they say, they suggest using SHA-512 from now on, SHA-3-512 for your hashing, so that your quantum computer cannot target it. You need about 1/3 the qubits to target a hash. And if you want to target a 256-bit hash, you need about 85.33 qubits. About 86 qubits, and we're already at like 70 qubits. So 256 is vulnerable. So, but with 512, you need about 171, right? So qubits. So that may still be a long time to go. So SHA-3-512 keeps whatever you're doing classically secure, prevents a quantum computer from breaking stuff. So, you can continue doing your work classically, just make sure your encryption happens in a higher dimension such that, or hashing happens in a higher dimension so that, a quantum computer, even with its potential, will not break. And then you don't have to worry about quantum computers. But if you want to use quantum computers, then you would do this. You would try to map your problem to a quantum computer, send QMI to the quantum computer, let it execute. And then you could also try to do quantum inspired software as well.
Okay, makes sense. Thank you.
Any more questions, guys?
I have just, this is Abhijit again. I have just one last question. So those physical quantum machines, right? The physical, the super cool cryogenic kind of machines, right? These gates you talked about, right? The C0 and the Hadad gates. Are those, so if suppose you have to do it in the physical machines, not using the the classical computers with the quantum inspired algorithms, then are those gates like built into those machines, or like I'm just trying to visualize what those machines, I mean, I understand, of course, there is There are all the pipes moving around with the cooling and all those things happening. But
So
what is
they
that
do
exactly?
is they have this kind of polarizer. It's like a green pyramidal thing, and it's say set at 45 degrees angle to the photons that are coming in, and so that causes the Bell states, the plus and minus states. That for plus and minus 45 degrees.
Okay.
So whenever you ask for it, then it will produce photons, put it to the polarizer, and the output photons would actually be in these Bell states that can be subsequently processed and things like that. Until then, you're not doing anything until you ask.
Based on the problem that we are going to solve, it has to be kind of configured that way.
Yeah.
Oh, okay.
Yeah.
So the equivalent, the qubits, the number of qubits and all, you have to configure it that way, basically.
Yeah. But what I'm saying is that maybe see what quantum algorithms are trying to do, and see if you can even classically have fun with it, right? Without even having to talk to a quantum computer. But all of these computers are available in the cloud, and get access to them as well and try out some fun stuff. And there are simulators available as well.
Okay. So like Google Cloud, are they available in Google Cloud?
Yeah, should be. I haven't tried it. Yeah.
Maybe Asif will know. I don't know.
There is a service that Google exposed, I believe, the D-Wave and so forth, right?
No, D-Wave, yeah. D-Wave exposes its own service. But Google, all of them have it on their respective clouds. Yeah. So you have to connect to the cloud and then ask for it. And usually, though, if you're in academia, you have more resources. But if you're not, I think they give you very limited resources, like the IBM quantum computer will give you a little bit of time, but it's still adequate to kind of fool around with it. But then after that, I think you have to pay for it. So.
And there's this whole emerging field of quantum machine learning.
So Asif, you want to throw some light on it?
That will be a big topic, perhaps a follow-up talk on it. But there's a very interesting intersection between quantum. Actually, all of these things are merging. The whole mathematics behind machine learning is so close to physics, and quantum is physics. So there's a gradual convergence now of all these things.
Yeah, that's fun, and it's kind of.
Okay, if enough people are interested, I would like to talk about quantum machine learning. It's a little bit far out there at this moment, a little bit away, but it's one of those things that you dream of today. You build a theory. By the time it becomes practical or real, it's another 10, 15 years.
Yeah, it should be fun. Yeah. We should explore.
Yeah, we should explore. Dilip, hey, thanks a lot. This was a most
thank you.
Just the right
you're welcome.
Practice and actual reality here. This is. I wish the audience could see you if your video worked.
Oh yeah, sorry about that. I don't know what the problem was. I think Asif put a photo there. So I still look like that. So.
Yes, in the video that we put advertising this talk. All right, guys. Thanks for
and thank you.
Thank you, Asif,
Bye.
for attending this. Thank you, Dilip, for the talk.
Thank you, Dilip. Very nice session. Thank you, Asif.
Oh. Hey.
Thank
you,
Asif.
Welcome.
Thank you, Asif sir.
Sure.
Thank you.
Thank you, Dilip. Thank you, Asif. Have a good day.
Thanks, Annie.
Thank you. Have a good day.
Bye.